Hey folks, I want to talk about LED grow lights and their efficiency. There's a couple of reasons that this comes to mind. First of which is the ever-increasing costs of fuel and transportation in agriculture, and the push for more localized agriculture to solve that part of that problem. And the second part of it is the ever-increasing costs of utilities. LED grow lights are kind of nifty. There's a couple of big things that they try and do is first get great growth rates because you're aligning the output of the LEDs with the photochemical efficiency curve of the plants so that you can get a really decent growth rate and you can save electricity in comparison with other sources of artificial light. The reason that occurs is this is a graph here of the photochemical efficiency of plants versus wavelengths. The efficiency along this axis and wavelength along this axis. Namely, plants are quite efficient at converting UV and blue light into photosynthesis, and likewise over here with dark red and red light for photosynthesis. Now green light, on the other hand, there's not much efficiency there, although certainly a plant can use some of it, but it starts to rise as we get over here into the red. If you look on the graph here, you'll see there's a purple, blue, green, amber, red, and dark red, and those are the spectral outputs of typical LEDs. Now, a couple things you might notice is that these peaks aren't aligned, and I've got a graph that shows that in a little bit more detail. Specifically, here's your blue LED, here's your peak, here's your typical red LED, and there's your peak. We can increase the efficiency of a grow light if we can shift these curves so that they more closely line up with what the plants can use. There's a number of ways we can look at doing that. Perhaps the simplest, although the least economically feasible, is to take advantage of the spectral curve variation of LED manufacturing. Namely, that the advertised spec here is at the peak, but you're going to have some that will operate at longer wavelengths here for the red or shorter wavelengths here for the blue. Of course, the economics is such as we got to buy 100,000 LEDs, you use 5,000 of them, and you got 95,000 left over, and what are you going to do with those? So it's not a real economical solution, but what one might want to do is discard this 5% of the LEDs, and I'm just guessing at the distribution, that are on the short wavelengths here in the red or the longer wavelengths here in the blue, and that would require incoming inspection and a certain allowance for scrap or alternative usage of the LEDs. Now, another thing we could do is we can look at red LEDs, and we see that if we're running them at colder temperatures, their output is higher, and as the temperature increases, the LED's output drops down. And it's also interesting to note that as the output drops, the spectral peak shifts. It shifts to the longer wavelengths, which is where we want it to be. It might be something that we could leverage for greater efficiency when it comes to LEDs. Of course, there's a balance in that. The harder you drive an LED, the less its electrical conversion efficiency to light becomes. So obviously there's a balance between a number of factors. Now in the blue range, things that operate a little bit differently. In the blue area, by changing the drive current, with a high drive current that's rated output, we achieve the spectral peak that is advertised. If we drop the drive current down, say we're down here to 75% or even 50%, the output drops, it gets dimmer, and also the wavelengths tends to go towards the longer part of the spectrum. Now there's a balance in that. We may want to run an LED at a lower power level to get better electrical efficiency, but if that shifts the wavelength, then we end up shooting ourselves in the foot. So there's a number of parameters that deal with control of LEDs that we could utilize to get much greater efficiency. Now some might say, this is all fine and good, but LED grow lights are really spendy, and that's true. But electricity costs, I've heard in California, with the progressive tiering of electrical usage, sometimes you might be hitting 40, 50 cents per kilowatt hour. All of a sudden, a greater cost of of a LED grow light. You may find that it pays for itself in short order, because in order to deal with these spectral shifts and output and all that, the control system would really need to close the loop, look at the spectral output and also look at the total luminous intensity. And I've got a way to do that, and I'm going to propose that in a future video, but I just wanted to kind of give you the background as to why I'm thinking this is something that needs to be looked at. Thanks for listening.